A cosmic fountain of pure energy erupts from the void. This is the white hole, a theoretical opposite to the all-consuming black hole. Physicist Carlo Rovelli once described it as what you would see if you ran a black hole movie backwards. By the end of this journey, you will understand how these hypothetical objects could fundamentally reshape our concept of reality. We will explore where the universe might be hiding these explosive portals and what bizarre materials they could be ejecting into the cosmos. How does something that only expels matter fit into a universe ruled by decay? Could our entire existence be the result of such an eruption? What do you believe is the most beautiful unsolved mystery of the cosmos? The equations were a revelation of pure geometry, describing gravity not as a force but as the curvature of the universe itself. When Karl Schwarzschild solved them to describe the gravitational field around a single point of mass, he gave the world its first mathematical portrait of a black hole. But mathematics has a curious habit of offering more than one answer. The same equations that described an object with a boundary of no return, the event horizon from which nothing escapes, also contained a perfect mirror image. This second solution described a region of spacetime with a boundary of no entry. It was a place where matter and light could only pour outward, erupting from a singularity that was forever sealed against the influence of the outside universe. This was the white hole, a theoretical object born from the symmetrical beauty of Einstein's own work. It presented a profound puzzle. If black holes were the ultimate sinks, draining matter from the cosmos, then white holes were the ultimate sources. But what could possibly fuel such a fountain? And if they are mathematical equals, why does our universe seem filled with one and utterly devoid of the other? This elegant duality, hidden in plain sight on the chalkboard, began a century-long quest to reconcile mathematical possibility with physical reality. That perfect mirror image from Einstein's equations reveals a cosmos built on a kind of balance. To truly grasp the white hole, we must first look clearly at the black hole, not just as a monster in the dark, but as a precise physical object. A black hole is a region of spacetime where gravity has won an absolute victory. At its edge lies the event horizon, a one-way membrane in the fabric of reality. Once anything, even a beam of light, crosses that threshold, it is pulled inexorably toward the central singularity. There is no return, no signal, no escape. The black hole is the universe's ultimate sink, drawing matter and energy inward forever. Now take that entire description and reverse it. This is the white hole. It too has an event horizon, but this boundary operates in the opposite direction. It is a surface of no entry. Matter and energy can stream outward from it, but nothing from the external universe can ever cross in. If you tried to approach a white hole, you would find it impossible to reach, as if space-time itself were pushing you away. Its interior is completely sealed off and inaccessible from our perspective. So while a black hole is a cosmic drain, a white hole is a cosmic spring, a theoretical fountain of creation. This creates a beautiful yet troubling symmetry. The mathematics treats them as equals, two valid solutions to the same profound equation, but our physical universe seems to have a strong preference. We see evidence for black holes everywhere, from stellar remnants to the supermassive giants at the centers of galaxies. White holes, however, remain entirely theoretical, never observed. This leads to a deep puzzle woven into the most fundamental laws we know. Physics has a powerful rule called the second law of thermodynamics, which states that disorder, or entropy, always increases in a closed system. A black hole fits this rule perfectly. It consumes ordered matter and increases the universe's overall disorder. But a white hole, by spewing out ordered energy, would appear to decrease disorder. It would be like a movie of an exploding building running backwards, showing the shattered pieces flying together into a pristine structure. This reversal seems to violate the universe's relentless march toward chaos. So we are left with a compelling question. If the math allows for this perfect opposite, and our cosmos is built on such symmetries, could black holes and white holes be two faces of the same entity? Are they perhaps connected in a way we cannot yet perceive, two phases of a single, unimaginable cosmic process? The search for an answer pushes us to look beyond the equations and into the quantum foam at the very edge of spacetime itself. The universe possesses a deep and relentless preference for disorder. This is not a metaphor but a fundamental law of physics, the second law of thermodynamics. In simple terms, it states that in any closed system, things naturally progress from a state of order to a state of chaos. A shattered glass does not reassemble itself. Heat always flows from a hot object to a cold one, never the reverse. This increase in chaos is measured as entropy, and the arrow of time itself seems to point in the direction of its relentless growth. Now consider our two cosmic objects through this lens. A black hole is a perfect servant of this law. It is the ultimate agent of disorder, consuming complex structures like stars and planets, breaking them down into their most basic constituents, and adding their mass to its own incomprehensible density. It is a one-way street leading to maximum entropy, but a white hole in its purest theoretical form appears to be a rebel against this universal decree. Imagine a geyser that erupts not with water, but with perfectly assembled intricate structures or with pure, coherent energy. It would be taking the disordered quantum foam of its hidden interior and transforming it into a pristine, ordered outflow. This is the thermodynamic paradox. A white hole seems to run the cosmic movie backwards, decreasing entropy locally by creating order from chaos. For decades, this was the central reason many physicists dismissed white holes as mathematical ghosts, beautiful impossibilities that could never manifest in a reality governed by the iron rule of increasing disorder. The great Stephen Hawking's pioneering work only deepened this puzzle. He showed that black holes are not cold, eternal tombs. They have a temperature. They radiate energy, albeit incredibly slowly, and they possess their own immense entropy. This revelation wove black holes seamlessly into the thermodynamic fabric of the cosmos. For a white hole to be taken seriously, it must find a way to fit into this same tapestry. It cannot be a magical source of free order. So how could such an object exist without breaking the universe's most cherished law? The answer may lie not in rejecting the white hole, but in reimagining its relationship with time and its dark twin. Perhaps they are not separate entities at all, but two phases of a single, breathtaking process, a cosmic cycle where the relentless growth of entropy is preserved on a scale grander than we can perceive. To solve this, we must venture beyond classical physics and into the strange, probabilistic world of quantum mechanics, where the very concepts of before and after begin to blur. Quantum mechanics introduces a rule that information, the unique identity of every particle, can never be truly destroyed. It can be scrambled, hidden, or transformed, but never erased from the cosmic ledger. This creates a direct conflict with the classical picture of a black hole. If matter falls in and is crushed into oblivion at the singularity, then the information it carried is lost forever. This is the black hole information paradox, a crisis that has divided physicists for decades. It suggests a fundamental flaw in our understanding, a place where general relativity and quantum mechanics give irreconcilable answers. To resolve this, we need a theory that can describe the extreme, microscopic conditions at the heart of a black hole. We need a theory of quantum gravity. Among the leading candidates is a framework known as loop quantum gravity. This approach proposes that spacetime itself is not a smooth, continuous fabric, but is woven from tiny, discrete loops. Picture the universe not as a blank canvas, but as an incredibly fine mesh, a network of a trillion threads of spacetime. At the everyday scale, this mesh is so fine it appears perfectly smooth, just as a piece of fabric feels continuous to your hand. But under the crushing pressure of a collapsing star, this quantum structure makes a profound difference. In the classical model, collapse continues unchecked, squeezing matter into an infinitely dense point, a singularity where the laws of physics break down. Loop quantum gravity suggests something else entirely. As collapse reaches its maximum possible density, the quantum weave of spacetime provides a sort of cosmic repulsion. Instead of reaching infinity, the process rebounds. The inward collapse stops, reverses, and begins to expand outward. From our distant perspective, watching from outside the event horizon, this transition would appear to take an almost unimaginable amount of time. But in the frame of the collapsing matter itself, the bounce could be nearly instantaneous. This is where the white hole emerges not as a separate object, but as the next phase in a cosmic life cycle. The black hole, in this view, is not an eternal tomb. It is a temporary state, a cosmic seed that, after a period of quantum gestation, blossoms into a white hole. The event horizon we see from the outside undergoes a subtle but radical transformation. It transitions from a point of no return to a point of no entry, as the interior geometry flips inside out and begins to expel all the matter and information it once consumed. This elegant idea does more than just rescue white holes from mathematical abstraction. It offers a potential escape from the information paradox. If a black hole eventually transforms into a white hole, then the information it swallowed is not lost. It is merely stored, incredibly scrambled and compressed, before being released back into the universe in that final explosive outflow. The information is preserved, satisfying quantum mechanics, while the transformative process maintains the relentless increase of entropy demanded by thermodynamics. The universe, in this radical picture, may be engaged in a form of cosmic recycling on the most extreme scales imaginable. But this leads to a new and even more bewildering question. If white holes are the reborn remnants of black holes, where in our observable universe could this breathtaking eruption be happening right now? But if a black hole's transformation into a white hole takes an almost unimaginable amount of time due to gravitational time dilation, where could we possibly hope to witness such an event? The answer may lie not in our present but in our distant past at the very dawn of time. The most promising place to look for a white hole is the primordial universe itself. In the first fleeting moments after the Big Bang, the cosmos was not the vast, cold expanse we see today. It was an unimaginably dense, hot, and turbulent sea of energy, a place where the very fabric of spacetime was subject to violent quantum fluctuations. In that seething cosmic foam, the distinction between a tiny black hole and a tiny white hole could have been blurred. According to some theoretical models, microscopic white holes could have spontaneously popped into existence from the raw energy of creation. These are called primordial white holes, and they would have been fundamentally different from the stellar mass objects we've discussed. They were not the end result of a star's collapse, but rather birthmarks of the universe, formed directly from the chaotic energy of its infancy. Their life cycle would have been incredibly brief. In the hot, dense environment of the early universe, these tiny white holes would have immediately begun ejecting their contents, releasing pent-up energy and perhaps even exotic forms of matter that no longer exist today. Imagine a pot of water just beginning to boil with tiny bubbles of steam erupting everywhere at once. The primordial cosmos might have been similarly frothing with these ephemeral fountains. Their explosive decay could have played a subtle but crucial role in shaping everything that followed. As they evaporated, each tiny white hole would have injected a localized burst of energy into the surrounding soup of particles. This could have created slight ripples in the density of matter, tiny seeds of inhomogeneity. Over billions of years, gravity would have amplified these seeds, pulling matter toward them, eventually forming the vast cosmic web of galaxies and galaxy clusters we observe. In this way, the ghostly fingerprints of primordial white holes might be imprinted on the large-scale structure of our entire universe. Furthermore, the exotic particles they ejected could hold the key to one of cosmology's greatest mysteries. Some physicists speculate that these decaying white holes might have been a factory for dark matter, the invisible substance that makes up most of the mass in the cosmos. If a white hole ejected particles that interact only very weakly with ordinary matter, they would stream through the early universe unseen, eventually clumping together under gravity to form the halos that now bind galaxies together. While this remains a speculative idea, it illustrates a profound shift in perspective. White holes are no longer just mathematical curiosities or the hypothetical end stages of black holes. They become potential architects, active participants in the construction of reality from its first moments. Their brief, brilliant eruptions in the cosmic dawn could have set the stage for everything that came after, from the first stars to the planet you are on right now. This connection transforms them from a footnote in theoretical physics to a possible key for understanding our own origins. Yet, if they played such a foundational role, could evidence of their existence still linger in the universe today, not just in the ancient past but in our present skies? The search leads us from the beginning of time to the most violent explosions we can currently observe. The galactic center is a cosmic maelstrom of unimaginable scale. Here, orbiting the supermassive black hole known as Sagittarius, a star, stars whip around at a fraction of the speed of light, and vast clouds of gas are torn apart by tidal forces in a perpetual, violent dance. It is a place where the laws of physics are stretched to their absolute limit, a natural laboratory for the most extreme phenomena in the universe. And it is here, within this chaos, that we might find the second potential signature of a white hole's explosive work. If the quantum bounce theory holds any truth, then the supermassive black holes anchoring galaxies like our own are not eternal. Given enough time, a span so vast it defies human comprehension, even these titans could undergo the transition. An ancient black hole in the core could have reached the end of its life cycle and rebounded into its white hole phase. The ejection of matter from such an object would be nothing like the steady trickle of Hawking radiation. It would be a catastrophic, high-energy event of almost biblical proportions. Imagine the entire accumulated mass of a supermassive black hole, everything it has consumed over billions of years, being converted and expelled in a directed eruption. This would not be a symmetrical explosion, but a focused jet channeled by intense magnetic fields and spin. So what would we see? Astronomers might detect an unexplained, ultra-bright flash of gamma rays emanating from the galactic center, a burst of energy so intense and brief it dwarfs any known stellar process. Or we might observe sudden, powerful outflows of particles streaming away at relativistic speeds, jets that appear without the typical accretion disk activity we associate with feeding black holes. These signatures would be temporary, perhaps lasting only days or weeks in observational terms, but their energy fingerprint would be unmistakably odd. The challenge, of course, is that the galactic center is already a festival of high-energy astrophysics. Brilliant flares from heated gas, collisions between stars, and the intense radiation from countless stellar remnants create a cacophony of signals. A white hole eruption would have to shout to be heard over this cosmic noise. It might even be masquerading in our data right now, catalogued as an unusual flare or an anomalous jet, its true nature waiting to be decoded. This transforms our view of the galactic core from a simple gravitational pit into a potential site of cosmic rebirth. The very engine that binds our galaxy together could, in a deep and theoretical sense, also be a fountain. The emptiest places in the universe may hold the quietest whispers of creation. Far from the brilliant chaos of galactic centers, beyond the sprawling webs of galaxies, lie the cosmic voids. These are the true deserts of space, regions spanning hundreds of millions of light years where the density of galaxies drops to almost nothing. It is a profound and haunting isolation, a near-perfect vacuum on a scale the human mind can scarcely comprehend. And it is here, in this overwhelming nothingness, that a third and perhaps most elusive form of white hole might reveal itself. Picture the life cycle of a tiny, primordial black hole, one formed in the universe's first frantic moments. If such an object survived to the present day and finally completed its unimaginably long quantum bounce, it would transition into a microscopic white hole not within a galaxy, but adrift in the immense, empty space between them. Its eruption would be a profoundly lonely event, with no surrounding gas clouds to ignite, no stars to interact with. The material it ejects would stream outward into a near-perfect void. The result would not be a brilliant flash visible across the cosmos, but something far more subtle. Think of a single firework detonating in an empty, pitch-black stadium. There is no crowd to gasp, no echo from nearby walls, just a brief, self-contained bloom of light, an expanding gas against an infinite backdrop of darkness. In the cosmic void, a white hole's outflow would create a faint, spherical shell of hot, ionized gas, gradually expanding and cooling as it journeys through the void. Detecting such an event borders on the realm of science fiction, yet it is not entirely impossible. Astronomers might one day spot a mysterious, point-like source of X-rays or radio waves that stubbornly refuses to match the signature of any known object. It would have no visible host galaxy, no companion stars, no discernible reason for being. Its energy spectrum would be anomalous, perhaps showing lines from elements in proportions never seen in supernova or quasars. It would be a ghostly beacon, a signal from a theoretical object singing its solitary song into the void. Finding it would be like searching for a single, unique grain of sand on a planet-sized beach. But the very difficulty of the search highlights a transformative idea. White holes are not merely endpoints for black holes or architects of the early universe. They could also be solitary wanderers, cosmic hermits whose entire existence plays out in the deepest silences between the stars. Their predicted signatures are so faint, so isolated, that they force us to confront the sheer scale of our ignorance. The next great discovery in astrophysics might not be a brilliant object in a crowded field, but a whisper from the darkest, emptiest corner of the sky. This leads us to a final, breathtaking possibility. If white holes can eject matter from a hidden quantum realm, what exactly might be streaming out from these cosmic fountains? Could it be the ordinary atoms of our world, or something far stranger, the very building blocks of reality itself? The architecture of a wormhole offers the most radical answer yet for where a white hole might eject its contents. For decades, wormholes have been a staple of science fiction, portrayed as shimmering tunnels or gateways that allow instant travel across the cosmos. But their theoretical foundation in physics is deeply intertwined with the very objects we have been exploring. The simplest mathematical model for a wormhole is known as an Einstein-Rosen bridge. It is not a tunnel you could walk through, but rather a short-lived connection in the fabric of spacetime itself. In this model, a black hole in one region of the universe is linked, through its interior singularity, to a white hole in another. Matter that falls into the black hole on one end would, in theory, be expelled from the white hole on the other. This transforms the white hole from a standalone fountain into an exit portal. Its ejection site is no longer a location you could simply point a telescope toward. It could be anywhere. The other end of this bridge might exist in a distant galaxy billions of light years away. It could even connect to a point in a different time, or in the most speculative models, to a completely separate universe altogether. The white hole becomes a cosmic doorway, and what it ejects is matter that has taken a shortcut through the hidden folds of reality. This idea pushes the concept to its absolute limit, but it comes with a profound caveat. The Einstein-Rosen bridge, as first described, is not a stable passage. It would snap shut faster than the speed of light, crushing anything attempting to pass through. For a wormhole to be traversable, to remain open long enough for matter or information to make the journey, it would require something truly exotic holding it open. Theoretical models suggest the need for a form of matter with negative energy density, a substance that creates gravitational repulsion instead of attraction. We have no evidence such a material exists or can be manufactured in the necessary quantities. Yet, even if the tunnel itself remains a theoretical impossibility, the architecture of the idea is compelling. The white hole end is not an optional feature, it is a fundamental component of the bridge's geometry. This means that if wormholes of any kind are woven into the structure of the cosmos, then white holes are too. Their ejection sites become the most unpredictable and untraceable of all. A brilliant flash of newly created matter in a void might not be from a local rebirth, but from a distant black hole's meal being delivered across the universe. While this remains the most speculative possibility, it completes a stunning picture. White holes could be the final stage of a black hole's life, the primordial seeds of structure, lonely eruptions in the void, or the exit points of cosmic shortcuts. Each role suggests a different form of matter streaming from their horizons. So what exactly might be pouring forth from these theoretical fountains? The answer could redefine the very substance of our reality. The very nature of a white hole suggests its output is not a simple return of what went in. If a black hole truly undergoes a quantum bounce, the matter it once consumed would be subjected to pressures and energies that defy all known physics. The complex structures of stars, planets, and gas clouds would be utterly erased, broken down into their most fundamental constituents. What erupts from the white hole horizon is not a replay of the past, but a new creation born from chaos. It is a primordial soup, a burst of raw cosmic ingredients. The most immediate and detectable signal would be an intense flash of high-energy radiation. Gamma rays, the most powerful form of light in the universe, would likely lead the charge, followed by X-rays and a torrent of ultra-fast cosmic rays. This initial blast wave would carry the unmistakable fingerprint of an event operating at the very edge of physical law, but the radiation is only the herald. Following it could be a spray of elementary particles, protons, electrons, neutrinos streaming outward as a hot, thin plasma. Some of the most speculative theories propose an even more exotic possibility. The transition itself might briefly forge forms of matter that do not exist under normal conditions. Quark-gluon plasma, a state that existed only in the first microseconds after the Big Bang, could be briefly recreated and ejected. Or perhaps dark matter particles, if they exist, could be manufactured in this quantum furnace and released into the cosmos. This connects back to the idea of white holes as potential architects, seeding the universe with the very substances that shape its large-scale structure. For astronomers, this theoretical profile is a crucial guide. It tells our telescopes what to listen for in the cosmic static. We are not searching for reassembled stars or recognizable nebulae. We are hunting for anomalous, short-lived bursts of the highest energy radiation with no clear source. We are looking for unexplained particle jets emanating from seemingly empty voids, or sudden, intense flares from galactic centers that lack the accompanying signs of normal accretion. The predicted signal is powerful but fleeting, a cosmic shout that fades quickly into the background hum of the universe. This transforms the challenge from a purely theoretical one into an observational puzzle. It means that data from gamma-ray observatories, X-ray telescopes, and cosmic ray detectors might already contain a faint, unrecognized signature, a ghost in the machine waiting for the right algorithm to reveal it. The search is not for an object but for an event, a brief and brilliant violation of the expected order. This leads us to a final, profound reflection. If such an event were ever confirmed, it would do more than just validate a century-old equation. It would force us to confront a new and startling vision of cosmic ecology, where death and rebirth are woven into the fabric of spacetime itself. The hunt for a white hole is a search for a ghost in the data. Astronomers, acting as cosmic detectives, are not looking for a stable object glowing in a telescope. They are hunting for an event, a brief and anomalous signature that defies every known catalog of celestial behavior. To find something that might not exist, you must first define what its impossible fingerprint would look like. The first key signature is a spectrum of pure, high-energy fury with no visible engine. Imagine detecting a brilliant source of gamma rays and X-rays, blazing with the power of a small galaxy. Your instruments swing toward it, expecting to see the telltale glow of a superheated accretion disk, the swirling banquet of matter that feeds black holes and neutron stars. But there is nothing, no disk, no companion star, no dense cluster of old stellar remnants. The radiation appears to be erupting from empty space itself, a fountain with no visible source. This absence is as critical as the presence of the light. A white hole, by its theoretical nature, does not consume, it only expels. Therefore, it should have no surrounding disk of infalling material, the universal dinner plate of high-energy astrophysics. Finding such a lonely, powerful beacon would send shockwaves through the field. The second signature is written in the language of time. White hole events are predicted to be transient, flashing into existence and then fading away. But their light curve, the precise graph of how they brighten and dim, would tell a unique story. It would not match the slow, majestic rise and fall of a supernova, where a star tears itself apart over weeks. It would also differ from the chaotic, millisecond spikes of a typical gamma-ray burst, which often signal the birth of a black hole. A white hole's light curve might show an incredibly rapid brightening, a plateau of sustained emission as the internal pressure releases, and then a smoother, slower decay as the eruption exhausts itself. It would be the birth cry of an object, not a death rattle. Telescopes that scan the sky nightly, like those hunting for kilonovas or asteroid impacts, are perfectly suited to catch these brief cosmic winks. An alert would go out, and every major observatory on Earth and in space would turn to coordinate, trying to capture the full spectrum of this dying echo before it vanishes forever. A third, subtler clue might come from the radio silence of the solar system. Networks of radio telescopes are constantly monitoring the sky, tracking everything from pulsars to passing asteroids. A white hole eruption, even a small one, would likely produce a burst of radio waves. If such a signal were detected, and it appeared as a new, compact point source that did not move against the background stars, it would immediately rule out a local object like an asteroid or comet. It would be a fixed point in the deep sky, screaming in radio frequencies for a short while before going quiet. Correlating this with a simultaneous X-ray or gamma-ray signature would build an irresistible case. These observational strategies perform a vital alchemy. They transform a beautiful philosophical idea, born from the symmetry of equations, into a testable, falsifiable hypothesis. They give our most advanced instruments, from the Fermi Gamma-Ray Space Telescope to the vast arrays of the Very Large Array, a specific ghost to chase. The search pushes technology and methodology to their absolute limits, demanding new ways to process data and recognize anomalies. In this meticulous, patient work, the greatest discovery would not be a simple confirmation. It would be the stunning realization that the universe contains a new class of event, one that rewrites the final chapter in the life story of a black hole and reveals a cosmos engaged in a form of quantum resurrection. This elegant symmetry in the laws of physics is more than a mathematical curiosity. It is a philosophical cornerstone. The fundamental equations that govern our universe, from the motion of planets to the bending of light, possess a remarkable property known as time reversal symmetry. In simple terms, if you were to take a perfect recording of any physical process, down to the dance of every atom, and play that recording backwards, the reversed movie would still obey all the laws of physics. A planet orbiting a star in reverse is just as valid a solution to gravity's equations as its forward motion. This suggests that at the deepest level, the universe's code does not have a built-in arrow of time. It treats past and future with a profound and unsettling equality. Now place a black hole into this picture. Its formation is a dramatic, one-way collapse. But if the underlying laws are truly time-symmetric, then the time-reversed version of that collapse must also be a valid physical possibility. And what is that? It is an expansion from a singularity, a fountain of matter erupting into being. It is the white hole. This is not a mathematical trick, but a logical imperative born from the bedrock of physics itself. The white hole forces us to confront a dizzying possibility. The irreversible flow of time we experience every day, with its shattered glasses and aging faces, might not be a fundamental feature of reality. Instead, it could be an emergent property, a large-scale illusion created by the specific, highly ordered starting conditions of our universe and the relentless statistical drive toward disorder. Our overwhelming experience of time's arrow is like watching a single drop of ink diffuse in a glass of water. You would never see it spontaneously gather back into a drop. Yet, the individual motions of every water and ink molecule are perfectly reversible according to the laws of physics. The irreversibility emerges from the unimaginable complexity of the system. So, if the white hole is the universe's way of showing us a reversed process, it challenges our most basic intuition. Could the cosmic movie, in isolated and extreme environments, actually run backwards? Could a region of spacetime exist where entropy decreases, where order emerges from quantum chaos? This is the profound philosophical weight the white hole carries. It is not merely an object, but a question about the nature of time itself. Is our unidirectional experience of cause and effect a universal truth, or is it a local condition, a story written only in the chapter of the cosmos we happen to inhabit? Accepting the white hole as a real possibility means accepting that the deep code of reality is far more symmetric and far stranger than the world it manifests. The silence of the cosmos is perhaps the loudest argument against them. If white holes are the brilliant, explosive endpoints of black holes, or even fleeting primordial fountains, why does our sky not blaze with their signatures? The universe is nearly 14 billion years old and contains upwards of 2 trillion galaxies. It is a stage of unimaginable scale and age, where even the rarest events should, statistically, have revealed themselves by now. This persistent non-detection is not a minor detail. It is a profound and legitimate challenge from the field of observational astrophysics. It forces us to confront the gap between elegant theory and stubborn reality. The absence of a clear white hole signal suggests several compelling possibilities, each reshaping what these objects might truly be. The first and most straightforward is that they are simply not there. Perhaps the mathematical symmetry is just that, a beautiful ghost in the equations with no physical counterpart, a road not taken by nature. Yet, given how deeply woven the concept is into the fabric of gravitational physics, many researchers explore more nuanced explanations. Perhaps white holes are not common because the process that creates them is incredibly slow. For a stellar mass black hole born from a collapsing star, the quantum bounce might unfold over timescales that dwarf the current age of the universe. Imagine a clock where the second hand ticks once every trillion years. From our fleeting human perspective, and even from the perspective of cosmic history so far, the clock would appear completely still. The black holes we observe might all still be in their long, dark gestation period, with their white hole rebirth scheduled for an almost infinitely distant future. In this view, the sky is silent because we are listening at the very beginning of the story. Another possibility is that the transition is not a singular, brilliant eruption, but a slow, dim leak. Instead of a catastrophic explosion, a white hole might dissipate its energy through a prolonged, quiet evaporation, a faint whisper of particles so subtle it blends seamlessly into the cosmic microwave background or the diffuse glow of interstellar space. Our telescopes are designed to catch the spectacular, the violent, and the bright, a process that releases its energy over billions of years in a form indistinguishable from background noise would be effectively invisible to us. There is also the chance we have seen them but mislabeled the evidence. The universe is a cacophony of high-energy events, gamma-ray bursts, supernova, quasars, and magnetar flares. A white hole's predicted flash could be hiding in plain sight within our existing catalogs, mistakenly filed under unknown type of transient or unusual gamma-ray burst. Without a definitive theoretical light curve to match against, these anomalies remain curiosities, not confirmations. This observational silence, therefore, is not an end to the search. It is a crucial constraint, a set of rules that any successful theory must obey. It pushes the idea away from the classical, long-lived fountain and toward the ephemeral quantum event. It suggests that if white holes are real, they are likely brief, rare, or so slow that their story is written in timescales we can scarcely comprehend. This challenge keeps the science honest, grounding a mind-bending concept in the hard, patient work of staring into the dark and listening for a signal that may never come. It transforms the white hole from a promised spectacle into a deeper mystery, one that asks us to question not just what we see, but when we are looking, and how the universe chooses to reveal its secrets. The ultimate white hole may not be an object in our universe, but the universe itself. This is the breathtaking leap some cosmologists have taken, connecting the quantum bounce of a single black hole to the grandest scale imaginable. What if the Big Bang, the singular event that birthed everything we know, was not a unique beginning from nothing, but the explosive white hole phase of something that came before? In this radical view, our entire cosmos, with all its galaxies and stars, could be the interior of a colossal white hole, erupting from a singularity that existed in a different parent universe. This transforms the Big Bang from a mysterious starting gun into a natural consequence of a deeper, cyclical physics. The mechanism is a direct scaling up of the quantum bounce. Just as a collapsing star might rebound into a white hole, an entire universe that has stopped expanding and begun to contract, a scenario called the Big Crunch, could reach a point of maximum density. Instead of collapsing into an eternal singularity, the quantum weave of spacetime at that scale could trigger a rebound, a cosmic scale bounce. The inward crunch reverses, and a new era of expansion begins. From the perspective of that new universe, this moment of rebirth would look exactly like a Big Bang, a hot, dense state exploding into being. Our universe, in this model, is not the first chapter, but merely the current volume in an endless cosmic library. This idea elegantly sidesteps the profound difficulty of explaining a true beginning from absolute nothingness. It replaces a singular creation event with a transformational one, where the death of an old cosmos becomes the birth of a new one. The white hole is no longer a hypothetical fountain in space, but the very structure of reality we inhabit. Its event horizon on this scale is not a boundary we could ever cross, but the limit of our observable universe, the point beyond which light from the parent cosmos could never reach us. This creates a profound and humbling picture of cosmic ecology. Just as a forest grows from the decay of previous generations, new universes may blossom from the remains of old ones. The laws of physics, the constants of nature like the strength of gravity or the mass of an electron, could be reshuffled in each bounce, meaning each new universe might operate by slightly different rules. Some might be stillborn, collapsing again immediately. Others, like ours, might find a stable balance that allows for complexity, stars, planets, and life to emerge. The search for evidence of such a cycle pushes cosmology to its very limits. Scientists look for subtle imprints in the cosmic microwave background, the afterglow of our own Big Bang, that might carry faint echoes or scars from a prior cosmic phase. They investigate whether the geometry of our universe shows signs of being part of a larger, connected structure. While definitive proof remains elusive, the power of this idea is not just in its answers, but in the questions it reframes. It suggests that the universe we call home might be part of a vaster, older process of renewal, where white holes are not merely objects within the story, but the very mechanism that writes new chapters across eternity. The quantum world operates on a principle of restless creativity. Empty space is never truly empty. According to quantum field theory, the very vacuum of spacetime is a seething, bubbling sea of potential. At unimaginably small scales and for fleeting instants, pairs of particles and their antiparticles spontaneously wink into existence, borrowing energy from the vacuum before annihilating each other and vanishing again. This is the uncertainty principle in action, allowing something to come from nothing, so long as it does not last long enough to be caught. This ceaseless dance of virtual particles is not just a curious footnote, it is the background hum of reality, responsible for effects we can measure, like the subtle shift in the energy levels of atoms. But if particles can do this, what about the fabric of spacetime itself? If the vacuum can briefly create a pair of electrons, could it also, for a vanishingly short moment, create a pair of connected distortions, a microscopic black hole and a white hole? This is the radical suggestion of quantum gravity. At the Planck scale, where distances are a trillion times smaller than an atom, spacetime is thought to lose its smooth, classical appearance. Instead, it resembles a frothing, turbulent foam. In this quantum foam, the geometry of spacetime is subject to violent, random fluctuations. Tiny wormholes could form, connecting different points. Microscopic black holes could pop into existence and evaporate almost instantly through Hawking radiation. And according to the same symmetry that gave us the classical white hole, their counterparts should exist here too. These would be virtual white holes, ephemeral eruptions of geometry where spacetime briefly turns inside out, acting as a source before the fluctuation collapses back into the vacuum. They are not objects you could ever hope to see or visit. Their lifetimes are staggeringly short, perhaps around 10 to the power of -43 seconds. They exist in a realm of pure potential, a statistical ghost in the equations, yet their theoretical existence is profound. It suggests that the distinction between a black hole and a white hole, so clear and absolute in Einstein's theory, becomes fundamentally blurred at the quantum level. In the foam, entry and exit, past and future, sink and source might be constantly interchanging. A virtual black hole might, in the very next instant, be a virtual white hole, its identity flickering like a candle flame. This paints a stunning picture of the universe's deepest foundation. The smooth, predictable spacetime we experience is not the fundamental reality. It is an average, a calm ocean surface that hides a turbulent, churning depths where the architecture of reality is constantly being rewritten on timescales too brief to comprehend. In this quantum sea, white holes are not rare, catastrophic events. They are an integral part of the fabric's very texture, as common and fleeting as the virtual particles that make up a vacuum. They become a necessary ingredient in the quantum recipe for gravity itself. This perspective offers a subtle but powerful resolution to the earlier paradoxes. If white holes are constantly flickering into and out of existence at the quantum level, then they are not rebels against the arrow of time, but participants in its statistical flow. Their brief, allowed existence does not violate the second law of thermodynamics because they are part of the quantum noise from which our classical, irreversible world emerges. They are the hidden gears in the clockwork, turning too fast for us to see, but essential to its steady, forward tick. So, while we may never detect a virtual white hole directly, the concept completes a magnificent symmetry. From the largest scales where our entire cosmos might be one, down to the smallest where they froth in the quantum vacuum, the white hole transitions from a hypothetical object to a fundamental feature of a coherent, if deeply strange, reality. This crisis is known as the black hole information paradox. Quantum mechanics, the rulebook for the very small, contains a sacred law. It states that information, the unique identity of every particle, its spin, its charge, its quantum story, can never be truly erased from the universe. It can be scrambled, hidden, or transformed beyond all recognition, but it must persist. This principle is called unitarity. Now, place a classical black hole into this picture. Matter falls in, crosses the event horizon, and is thought to be crushed into oblivion at the singularity. If the black hole then evaporates completely via Hawking radiation, which is theorized to be purely thermal and random, then that unique information appears to be permanently deleted. It is as if you burned a complex handwritten novel and all that remained was generic heat and ash. The story is gone. This creates a direct and violent contradiction between the smooth geometry of general relativity, which allows the singularity, and the unwavering rules of quantum mechanics, which forbid information loss. For decades, this paradox has represented a fundamental fault line in our understanding of reality. Something has to give. The white hole, particularly in the quantum bounce model, offers a graceful and elegant solution. Think of the black hole phase not as a tomb but as a cosmic processor. When matter falls in, its information is not destroyed. Instead, it is imprinted onto the quantum structure of the event horizon, a concept known as the holographic principle, where all the data of a three-dimensional volume can be encoded on its two-dimensional boundary. The information is incredibly scrambled and compressed, but it is preserved. Now, during the quantum bounce transition to the white hole phase, this processor begins to run in reverse. The stored information is unfurled, reprocessed, and woven back into the outflow of particles and radiation erupting from the white hole horizon. The information is returned to the universe, not as a reassembled star, but encoded in the correlations and relationships between the ejected particles. In this narrative, the white hole is the universe's mechanism for cosmic recycling on the most fundamental level. It ensures that no quantum story is ever permanently lost, only temporarily archived in the most extreme conditions imaginable. Therefore, the search for white holes transcends a hunt for a strange astrophysical object. It becomes a quest to verify the consistency of the universe's own laws. Finding evidence for a white hole or for a process like the quantum bounce would not merely add a new entry to the catalogue of celestial phenomena. It would be a monumental step toward resolving one of the deepest theoretical crises in modern physics. It would demonstrate that quantum mechanics holds firm even at the edge of a singularity, and that the universe has a way of preserving every scrap of its history, no matter how violently it seems to be erased. The white hole, in this light, is the potential guardian of quantum certainty, a hidden mechanism ensuring that no story in the cosmos is ever truly forgotten. Einstein's general relativity is not the final word on gravity. While it passes every test we have thrown at it, from the orbit of Mercury to the bending of light around galaxies, scientists know it is incomplete. It cannot describe the singularity at the heart of a black hole, and it remains stubbornly separate from the quantum world. This has led physicists to explore what lies beyond Einstein's masterpiece, to consider modified theories of gravity. And within these alternative frameworks, the white hole emerges not as a quantum afterthought, but as a natural, even inevitable, feature of the cosmos. One prominent direction is known as F of R gravity. In this family of theories, the equations are extended by adding new mathematical terms that depend on the curvature of spacetime itself. Think of it like upgrading a simple, elegant map of a mountain range. The original map shows the peaks and valleys accurately, but the new version includes details about how the rock itself twists and compresses under pressure. These extra terms change how gravity behaves in the most extreme environments. In some versions of F of R gravity, the equations that describe a collapsing star do not lead to a point of infinite density. Instead, the new terms create a powerful repulsive force that halts the collapse before a singularity forms. The inward fall hits a barrier and rebounds outward. What you get is a white hole solution built directly into the classical equations, without ever needing to invoke quantum mechanics. It is a smooth, continuous process predicted by a modified law of gravity. Another fascinating path is Einstein-Cartan theory. This framework introduces a new property to the fabric of spacetime called torsion. In Einstein's original theory, spacetime is like a flexible rubber sheet that curves in the presence of mass. In Einstein-Cartan theory, it is more like a flexible sheet that can also twist. This twist or torsion arises from the intrinsic spin of quantum particles. When you have a tremendously dense object like a collapsing star, this torsion can build up to incredible levels, becoming a sort of cosmic spring. At the moment of maximum compression, the pent-up torsion releases, pushing back against the collapse and triggering an expansion. Once again, the result is a classical white hole, born from the geometry of a spinning, twisting spacetime. These alternative theories are not mere mathematical exercises. They produce white holes with potentially different, observable signatures. A white hole from an F of R gravity model might have a longer, more stable lifetime than a fleeting quantum bounce. One born from torsion in Einstein-Cartan theory might eject matter with a distinct spin polarization, a unique fingerprint in the particles it emits. By exploring these possibilities, researchers are not just hunting for one kind of object. They are testing the very laws that govern the universe. The persistence of the white hole concept across such diverse theoretical landscapes is telling. It suggests that the idea of a cosmic fountain, a region of expulsion, is a robust feature that appears whenever we try to push our understanding of gravity beyond its known limits. Whether through quantum loops, modified curvature, or spacetime torsion, the white hole refuses to disappear. It stands as a versatile and compelling clue, a signpost pointing toward a deeper, more complete theory of everything, waiting in the data of some future, impossible explosion. The invisible scaffold of the cosmos presents its own profound riddle. We call it dark matter, a substance that does not emit, absorb, or reflect light, yet its gravitational pull is the hidden architect of our universe, sculpting galaxies and guiding their motion. For decades, its true identity has remained frustratingly out of reach. Could the white hole, a theoretical fountain of creation, offer a clue to this other great mystery? One speculative but fascinating hypothesis proposes a direct link. Perhaps the matter ejected from a white hole is not the ordinary atomic stuff we are made of, but something far more exotic. The quantum processes at the heart of a bouncing singularity might manufacture particles that are stable, massive, and interact with ordinary matter only through gravity and perhaps the weakest of forces. These would be ideal candidates for dark matter, In this scenario, primordial white holes, those fleeting fountains from the universe's first moments, would not have just ejected radiation and plasma. Their final bursts could have seeded the cosmos with a persistent rain of these ghostly particles. As these particles streamed out, they would have cooled and spread, eventually clustering under their own gravity to form the vast, invisible halos that now cradle every galaxy. This idea provides a compelling alternative to the standard thermal production story for dark matter. Instead of emerging from a hot, dense soup of particles in the early universe, dark matter could be a kind of cosmic ash, the cooled remnant of countless quantum eruptions from the dawn of time. While this remains highly conjectural, the elegance of the connection is powerful. It suggests that two of cosmology's deepest puzzles might share a single, breathtaking solution. The search for white holes then becomes indirectly a search for the origin of the universe's hidden mass, turning every anomalous flash in the data into a potential clue about the glue that holds reality itself together. When direct observation remains just beyond our reach, science turns to the art of digital creation. Supercomputers have become our cosmic laboratories, allowing us to simulate realities we cannot yet touch. This is the domain of computational astrophysics, where the equations of Einstein are translated into rivers of ones and zeros, building virtual universes to test our boldest ideas. Researchers use a sophisticated tool called numerical relativity to tackle this challenge. You cannot solve Einstein's complex field equations with pencil and paper for a dynamic, erupting white hole. Instead, scientists break down the fabric of spacetime itself into a vast, three-dimensional computational grid. Each point in this digital mesh calculates the local curvature of spacetime, how it warps and flexes in response to the simulated mass and energy of a white hole. It is like constructing a breathtakingly detailed flight simulator for the laws of gravity. These simulations allow us to model scenarios that are pure mathematical ideals. We can watch in accelerated time how spacetime behaves just outside the event horizon of a white hole. We can see how the fierce gravitational repulsion would push against any infalling gas or dust, creating shock waves and turbulent outflows. Crucially, these virtual experiments can predict the symphony of gravitational waves such an object might produce. The violent birth of a white hole from a quantum bounce, or the sudden ejection of a massive shell of matter, would send ripples through the simulated spacetime. The supercomputer calculates the frequency and amplitude of these ripples, generating a theoretical waveform. This synthetic data is a treasure map for observatories like LIGO and Virgo. It gives them a specific pattern to listen for in the constant, faint hum of the cosmos. Without these simulations, a strange gravitational wave signal might be dismissed as noise or an unknown black hole merger. With them, astronomers have a specific, if hypothetical, template to compare against the data. These digital universes also model how ordinary matter would react. If a white hole erupted within a cloud of interstellar gas, the simulation shows how the blast wave would propagate, how the gas would be heated and ionized, and what light it would emit across the electromagnetic spectrum. This creates a full spectral fingerprint from radio waves to gamma rays that survey telescopes can hunt for. The power of this approach is that it moves the search from pure speculation to a data-driven investigation. It transforms the white hole from a philosophical concept into a set of quantifiable, observable predictions. While the simulation is not reality, it is a rigorous exploration of possibility, defining the very signatures that might one day turn a theoretical ghost into a discovered fact of our universe. The equations give us the mathematics, but the mind gives them meaning. White holes resonate far beyond the chalkboard, touching something ancient within our collective imagination. They are not merely astrophysical proposals, they are powerful modern symbols. At their core, they represent the ultimate triumph of emergence over entropy, a cosmic defiance of the inevitable decay that seems to govern everything from stars to living cells. They offer a narrative of pure creation, a fountain where something comes from what appears to be nothing, echoing our oldest myths of Genesis and renewal. This symbolic power has naturally flowed into the stories we tell ourselves. In science fiction, literature, and film, white holes and their conceptual cousins are rarely portrayed as sterile mathematical objects. Instead, they become mystical portals, gateways to other dimensions, or bridges to different eras. They are the ultimate plot device for rebirth and second chances, a literal exit from one reality into another. This storytelling instinct reveals a deep human fascination. We are drawn to the idea that an end is not absolute, that a collapse can be followed by an expansion, that information and perhaps even essence can be preserved through the most violent of transitions. Philosophically, the white hole delivers a quiet challenge to a strictly deterministic view of the cosmos. A universe containing only black holes is a universe on a one-way street toward a cold, dark, and silent future. It is a story with a predictable, if distant, ending, but introduce the possibility of white holes, and the narrative fractures into something more complex and open-ended. It suggests a cosmos that is not merely a clock winding down, but perhaps an engine of cyclical transformation. It introduces the radical notion of spontaneous generation at the grandest scale, where new possibilities can erupt from the ashes of the old. This cultural and philosophical resonance is not a side effect of the science, it is part of its lifeblood. It shows how the most cutting-edge theoretical work feeds our fundamental need for metaphor. We use these concepts to frame our own experiences of loss and recovery, of endings that seed new beginnings. The white hole, in the end, becomes more than an object we might find. It becomes a lens through which we can reimagine the very nature of existence, asking if the universe itself holds a capacity for surprise, for renewal, and for stories that never truly end. Roger Penrose, a titan of theoretical physics, offers a powerful and elegant objection. He argues that a classical white hole in our universe would be fundamentally unstable. Picture a theoretical fountain of pure energy, an object that by definition cannot accept anything from the outside. Now imagine a single speck of interstellar dust, a tiny molecule of hydrogen, drifting toward it. According to Penrose, the very act of this external matter approaching the white hole's event horizon would alter the surrounding geometry of spacetime. The gravitational influence of that incoming speck would be enough to tip the delicate balance. The region of no entry would collapse, transforming almost instantly into a region of no return. In this view, a white hole is a cosmic impossibility, a mathematical phantom that could never survive contact with the messy, material reality of the cosmos. It would be like a perfect soap bubble, beautiful in theory, but doomed to pop the moment it touches the air. This criticism strikes at the heart of the classical white hole model. If true, it means that even if such an object formed, it could not persist. It would be a transient glitch, immediately overwritten by the universe's relentless gravitational logic, becoming the very thing it was meant to oppose. The objection is not easily dismissed. It comes from applying the same rigorous general relativity that predicted black holes to their hypothetical twins and finding a fatal flaw in their longevity. This forces a crucial refinement. Perhaps white holes cannot exist as long-lived classical structures in an otherwise matter-filled universe. But what if they are not classical? What if their existence is inherently quantum, tied to a moment of transition so brief that Penrose's instability argument does not have time to take hold? The quantum bounce model, where a black hole transitions and ejects its contents rapidly, sidesteps this by making the white hole phase an ephemeral event, not a permanent object. The fountain erupts and dissipates before the outside universe can react to collapse it. A second, more philosophical criticism challenges the very foundation of the time reversal argument. Yes, the fundamental laws of physics are time-symmetric, but our universe is not. It began in a state of remarkably low entropy, an incredibly ordered and specific configuration often called the Big Bang. This initial condition is not explained by the time-symmetric laws. It is a boundary condition, a starting point imposed upon them. You can run the equations of gravity backwards from a collapsing star and get a white hole, but you are starting from a highly ordered, low-entropy state, the intact star. The real universe's arrow of time emerges from this mysterious initial low-entropy condition. Critics argue that simply reversing the equations is a mathematical trick that ignores this profound asymmetry baked into cosmic history. A white hole as a time-reversed black hole would require the universe to provide a similarly low entropy, finely tuned starting condition for the eruption itself, which seems just as inexplicable as the original Big Bang. Engaging with these counterarguments is where real science thrives. It is not a sign that the idea is failing, but that it is being taken seriously. Each pointed critique is a whetstone, sharpening the theory and forcing its proponents to build more robust, more nuanced models. The instability problem pushes theorists toward quantum, transient descriptions. The entropy objection encourages deeper investigations into cosmology and whether a prior cosmic phase could naturally provide the conditions for a white hole eruption. This rigorous back and forth is the engine of discovery. It ensures that the white hole is not just a captivating story, but a hypothesis that must withstand the most severe logical stress tests the scientific community can devise. The journey to understand these cosmic fountains is paved with such necessary skepticism, each challenge making the eventual destination, whether confirmation or rejection, far more meaningful. The silence we currently hear may simply be a limitation of our instruments, our best chance to hear a cosmic fountain, or to finally confirm its absence, lies with the next generation of telescopes now being built. These are not just incremental upgrades, they are revolutionary new senses for humanity, designed to listen for whispers we have never before been able to perceive. The Vera C. Rubin Observatory, currently under construction in Chile, represents a fundamental shift in how we watch the sky. Instead of focusing on a single deep field, its enormous camera will scan the entire visible sky every few nights, creating an ultra-high-definition movie of the cosmos. It will catch anything that changes, flickers, or erupts. A white hole's predicted brief flash, a sudden point of light where none existed before, would be an instant candidate in this vast digital net. The observatory's relentless gaze offers our first real hope of catching one of these elusive events in the act, transforming a needle in a haystack search into a systematic, data-driven hunt. While Rubin scans for the flash, the James Webb Space Telescope offers a different kind of vision. Its profound sensitivity in the infrared spectrum allows it to see the cold aftermath of cosmic violence. Long after a white hole eruption's brilliant gamma rays have faded, the ejected shell of material would expand and cool, eventually glowing faintly in infrared light. Webb could potentially detect these ghostly, cooling remnants in distant voids or at the hearts of galaxies, studying their composition to see if they match the predicted primordial soup. It could analyze the light from such a shell and tell us if it contains the exotic elements or unusual particle signatures theorists have proposed. Perhaps the most tantalizing new window will open with space-based gravitational wave astronomy. Projects like the Laser Interferometer Space Antenna, or LISA, aim to launch a trio of satellites into orbit, forming a gravitational wave observatory millions of miles in size. Free from Earth seismic noise, LISA will listen for the low-frequency ripples in spacetime that ground-based detectors like LIGO cannot hear. These are the frequencies where the most massive events in the universe sing. The formation of a supermassive black hole, the merger of gigantic galactic cores, or the violent birth tremor of a white hole from a quantum bounce could all produce a unique gravitational wave signature. LISA data would provide a direct soundtrack to such extreme geometry, offering evidence that is not based on light, but on the shuddering of spacetime itself. Together, these new tools provide something we have never had before, a multi-messenger portrait of the cosmos with unprecedented depth and clarity. They will generate oceans of data, and within those digital seas may lie the subtle, anomalous signal that defies all other explanations. This is the practical future of the search. It moves the question from the realm of pure theory into the domain of hard, observational evidence. Within the next decade or two, these silent sentinels will either deliver the first glimpse of a white hole's eruption, or they will place such stringent limits on their existence that we will be forced to reconsider the universe's fundamental symmetry in a profound new way. The wait for an answer is almost over, and the tools to find it are finally taking shape. Our universe might be just one room in an infinite cosmic mansion. This is the multiverse, a breathtaking concept that proposes our reality is but a single bubble in a vast, frothing sea of other universes, each with its own unique laws and history. And within this grand theoretical framework, the humble white hole finds a role of staggering importance. No longer merely a fountain in our own cosmos, it could become a gateway, a birth canal, or even a cosmic sculptor on the grandest possible stage. The connection is most direct through the wormhole model. If a white hole is one end of an Einstein-Rosen bridge, the question of where the other end lies becomes profound. It might not simply lead to another point in our own universe. The equations allow for the possibility that the tunnel could connect to a completely separate spacetime continuum, a different universe altogether. In this view, a white hole eruption we might observe would not be the rebirth of a local black hole, but the arrival of matter or energy from a parallel reality, a leak in the walls between worlds. The white hole becomes a natural puncture in the fabric of a multiverse, a one-way valve where the physics of another realm briefly spills into our own. This idea expands even further within certain interpretations of string theory, a leading candidate for a theory of everything. String theory suggests the existence of many extra, curled-up dimensions of space. The way these dimensions are configured determines the fundamental constants of a universe, like the strength of gravity or the mass of an electron. This gives rise to what theorists call the landscape, a vast, abstract terrain of possible universes, each with a different set of physical laws. Within this landscape, a white hole could be more than a gateway, it could be a creator. Imagine a quantum fluctuation in the multiversal foam giving rise not just to a particle pair, but to an entire baby universe. This new cosmos would inflate rapidly, pinching off from its parent reality. From the outside, from the perspective of the parent universe, this event might appear as the sudden, brief eruption of a white hole, a point spewing out the raw energy that becomes an entire new reality. For the inhabitants of that newborn universe, however, their entire Big Bang would be the interior of that white hole, expanding forever. This elevates the white hole from a curious astrophysical object to a potential mechanism of cosmic reproduction. It becomes a seed pod for new realities, a natural process by which the multiverse proliferates and evolves. Each new bubble universe could inherit, through the chaotic physics of its birth, a slightly different set of physical constants from its parent. Some would be stillborn, collapsing instantly. Others, like ours, would find a stable, fertile balance that allows for galaxies, stars, and life. In this breathtaking picture, the white hole is not just an exit, it is an origin. Studying them, therefore, becomes about more than understanding our own universe's oddities. It becomes a way to investigate the very rules of cosmic genealogy. If such a process is real, then the white holes we might one day detect could be the umbilical cords of sibling universes, their faint signals telling us not about the death of stars, but about the vibrant, branching family tree of all that exists. This transforms the search from a local mystery into a quest with truly universal implications. These cosmic fountains offer a unique kind of classroom. Beyond their potential role in the cosmos, white holes hold immense value as a teaching tool, a brilliant device for illuminating the deepest and most counterintuitive ideas in physics. They transform abstract mathematical principles into a compelling narrative, a story of paradox that forces students to question everything they think they know about reality. The journey begins with a simple, elegant symmetry. Introducing a white hole immediately makes a student confront the time reversal symmetry of physical laws. They must grapple with the dizzying idea that the fundamental equations governing planets and particles treat past and future as equals. This leads directly to a discussion of entropy and the arrow of time, pushing them to ask why we only experience time flowing in one direction if the underlying laws are so symmetric. The white hole becomes the perfect counterexample, the what if that clarifies the rule. It makes the strange, statistical nature of time's arrow tangible. From there, the tool demonstrates the majestic structure of general relativity. Students can trace the logic from Einstein's field equations to Schwarzschild's solution, seeing how one set of principles naturally gives birth to two mirror-image objects. They learn that mathematics can reveal possibilities beyond our initial imagination, and that science often progresses by taking its own tools seriously, even when the results seem fantastical. The inevitable paradoxes then become the engine for deeper learning. When students realize a white hole seems to violate the second law of thermodynamics, they are not encountering a dead end. They are standing at the frontier. This conflict forces them to examine the assumptions behind the law itself and to explore potential resolutions like the quantum bounce or the holographic principle. They are no longer passive recipients of knowledge. They are active participants in a live scientific debate, weighing evidence and theoretical models. In this way, the white hole acts as a perfect bridge. It connects the deterministic, geometric world of classical general relativity with the probabilistic, fuzzy realm of quantum mechanics. By wrestling with the information paradox, students see first, and why these two pillars of modern physics are incompatible, and why a theory of quantum gravity is the holy grail of fundamental science. The object itself is the unanswered question, and its mystery vividly illustrates how science advances not by having all the answers, but by learning how to ask better questions. Ultimately, contemplating white holes trains a specific and vital kind of intellect. It requires holding two contradictory ideas in mind at once, thinking in scales both vast and infinitesimal, and accepting that the universe may not conform to human intuition. This abstract, counterintuitive thinking is the very bedrock of theoretical physics and cosmology. By engaging with this elegant thought experiment, students and curious minds alike exercise the mental muscles needed to explore the true wonders of our reality, preparing them for the next great paradox that will inevitably emerge from the dark. There is a quiet poetry woven into the mathematics of our universe. Beyond the raw data and observational evidence, many of the greatest breakthroughs in physics have been guided by a subtle, almost artistic principle, a sense of beauty. Theorists often speak of an idea's elegance, its simplicity, or its symmetry as a compass pointing toward truth. The white hole, in this light, is not just a prediction, it is a completion. It offers a perfect yin to the black hole's yang, restoring a balance that feels inherently right within the equations. This aesthetic drive for symmetry has a storied history. Paul Dirac's equations demanded the existence of a mirror image for the electron, leading him to predict antimatter years before it was ever observed in a laboratory. Albert Einstein spent decades pursuing a unified field theory, driven by a profound belief that nature's forces should emerge from a single, harmonious framework. The search for white holes is animated by this same deep-seated intuition. It is the pursuit of a cosmic balance sheet, where every sink has a potential source and every ending holds the seed of a beginning. We are drawn to the idea not merely because the math allows it, but because a universe that contains such a flawless symmetry feels more complete, more intellectually satisfying. It suggests that at its core, reality operates on principles of profound and beautiful coherence, even in the violent, alien realms of singularities and event horizons. This aesthetic longing is a powerful engine for discovery, reminding us that our quest to understand the cosmos is as much about seeking harmony as it is about cataloging facts. The quest to understand a cosmic fountain is reshaping our most advanced computers. While telescopes scan the skies for a white hole's flash, an equally profound search is unfolding in the abstract realm of quantum information science. Here, the theoretical crisis of information falling into a black hole has become a fertile testing ground, forging an unexpected bridge between astrophysics and the quest to build a quantum computer. The core challenge is the same. How is information preserved when it enters an object that seemingly destroys everything? To solve this, physicists have begun to model a black hole, and by extension a white hole, not as a smooth geometric object, but as the most complex quantum system imaginable. They describe its event horizon as a vast collection of entangled quantum bits, or qubits. Each qubit represents a tiny fragment of the information about everything that has fallen in, scrambled and stored in the quantum fabric of the horizon itself. In this view, the black hole is not a tomb, but a chaotic, fast-scrambling quantum processor. The transformation to a white hole phase then becomes a specific kind of quantum computation, a complex decoding process where those scrambled qubits are gradually transformed into the outgoing radiation and particles of the eruption. This perspective uses the tools of quantum computing to tackle gravity's greatest paradox. Concepts like quantum error correction, which protects fragile qubits from decoherence in a lab, are now applied to the horizon of a black hole. The idea is that information is not lost inside the singularity, but is instead error-corrected and hidden within the correlations of the Hawking radiation, awaiting the white hole phase for its final release. This cross-pollination of ideas flows both ways. The extreme physics of black holes and white holes presents natural problems of immense computational complexity, pushing theorists to develop new algorithms and understandings of how quantum information can be stored and retrieved. Pondering these cosmic objects has led to concrete insights in quantum information theory, suggesting that the universe itself might be performing a form of quantum error correction on a scale we are only beginning to comprehend. The white hole, therefore, exists at a fascinating intersection. It is a potential astrophysical event, a key to a theoretical paradox, and now a source of inspiration for the next technological revolution. By studying how information might survive a journey through spacetime's most violent transformation, we are not just learning about the cosmos, we are uncovering deeper principles about information itself, principles that may one day power the computers of tomorrow. The allure of a cosmic fountain can sometimes outrun the facts that describe it. As white holes capture our collective imagination, a vital part of the scientific journey is to gently separate the thrilling speculation from the grounded theory, ensuring public wonder is built on a foundation of clarity. A common and understandable misconception is that a white hole would be a source of anti-gravity, a place where the rules of attraction are flipped. In reality, gravity near a white hole is still powerfully attractive, pulling objects toward it just as any massive object would. The magic, or rather the physics, is in the geometry of its event horizon. It is not that gravity pushes you away, It is that the fabric of spacetime is structured in such a way that crossing that boundary from the outside becomes impossible. Think of it like trying to paddle a canoe up the side of a waterfall. The water is still flowing down, obeying gravity, but the sheer vertical rush creates a barrier your canoe cannot overcome. The white hole's horizon is a similar barrier in spacetime itself. Another crucial point is their status. White holes are not proven to exist. They are a compelling, elegant, and mathematically sound prediction that emerges from our best theories, but they remain entirely hypothetical. The search is ongoing, and their theoretical nature is not a weakness of the idea, but an honest reflection of where the science currently stands. It is the difference between a meticulously drawn treasure map and the chest itself. The map, based on all known clues, tells us where to look and fills us with excitement for the hunt, but the discovery is still ahead of us. This leads to a third, more practical clarification, often fueled by science fiction. The energies involved in any realistic white hole scenario would be beyond apocalyptic. The radiation, the tidal forces, the sheer violence of the quantum processes at play would reduce any known material, including a hypothetical spacecraft, to its most fundamental particles instantly. They are not portals for travel, but rather subjects for remote, awe-inspired study. Addressing these points is not about dampening enthusiasm, but about deepening it. When we engage with the cosmos clearly, distinguishing between established fact and brilliant conjecture, we build a shared trust in the scientific process. It allows everyone to participate in the genuine mystery, to marvel at the predictions of our equations while understanding the patient, collective work required to test them. This clarity transforms public wonder from a passive consumption of spectacle into an informed partnership in the greatest detective story of all, the ongoing investigation of reality itself. This pursuit of knowledge, even for an object we may never touch, asks something profound of us. Why should society dedicate precious resources, fund complex telescopes, and support brilliant minds in the search for something that may not exist and promises no immediate practical return? The question is not about budgets but about our identity. Investigating white holes is a form of pure research, a quest driven not by the promise of a new gadget, but by the fundamental human need to understand the architecture of our reality. It is an investment in our intellectual and cultural capital. The tools we build to listen for gravitational waves or to simulate quantum spacetime are marvels of engineering that push the limits of computation and materials science. The minds trained in this rigorous, abstract thinking often go on to solve concrete problems in fields from medicine to data security, their creativity honed on the hardest puzzles the universe can offer. History is filled with such unexpected gifts. The equations developed to describe curved spacetime around black holes are now essential for the precision of global positioning systems, ensuring your map application knows exactly where you are. The pursuit of one mystery so often unlocks solutions to another we had not yet even conceived. But beyond these tangible spin-offs lies a deeper, more philosophical return. This kind of exploration fulfills a core aspect of what it means to be human. We are the species that looks at the stars and asks why. We are driven to map the boundaries of the possible, to know what lies in the darkness beyond the campfire's light. Funding such research is a statement of values. It says that as a civilization, we value curiosity for its own sake. We believe that expanding the horizon of human understanding is a worthy endeavor, one that enriches our collective story and gives context to our fleeting existence. The search for a white hole, then, is more than astrophysics. It is a chapter in the oldest story we tell, a testament to our refusal to accept ignorance as a final answer, and a commitment to leaving a legacy of wonder for those who will look up long after we are gone. The idea of a white hole first flickered into public consciousness not through a physics journal, but through the pages of speculative fiction. For decades, they served as convenient narrative shortcuts, magical portals, or unexplained cosmic wonders that propelled characters across galaxies or into alternate dimensions. They were plot devices unburdened by the harsh constraints of mathematics or thermodynamics, representing the ultimate in science fantasy where anything could erupt from anywhere. This pop culture infancy, however, was not a dismissal of the concept, but rather its first germination. It proved the idea held a powerful grip on the human imagination, a symbolic answer to our longing for gateways and second chances. The serious scientific journey began when someone dared to take that fantasy and ask if the universe's own rulebook might allow for it. That rulebook was Einstein's theory of general relativity. As the profound implications of his equations spread through the academic world in the mid-20th century, physicists realized the symmetry was already there, waiting in the mathematics. The white hole was not an invention, it was a discovery hidden within the logic of gravity itself. This marked a critical pivot. The concept moved from the realm of magical thinking to the realm of mathematical possibility. It was no longer a writer's tool, but a physicist's puzzle, a legitimate solution that demanded an explanation for its apparent absence from our reality. The transformation deepened with the rise of quantum gravity research, when theorists began wrestling with the information paradox and the nature of singularities. The white hole evolved from a static, classical oddity into a dynamic component of potential solutions. In frameworks like loop quantum gravity, it became a phase, a natural outcome of a quantum process rather than a standalone object. This evolution from sci-fi trope to scientific frontier is a profound case study in how knowledge advances. It demonstrates that the initial spark of an idea, no matter how outlandish it seems, can be invaluable. Imagination provides the destination, the what if that pulls us forward. Rigorous mathematics then builds the road, testing every step, ensuring the journey is not a flight of fancy but a logical progression. The white hole's story blurs the line between inspiration and investigation, reminding us that the future of physics is often dreamed in broad, bold strokes long before it is meticulously calculated. It suggests that our most creative stories about the universe might not be mere entertainment, but early, intuitive maps of territories we have not yet learned to measure. Before a single telescope is pointed at the sky, the journey begins inside the human mind. This is the domain of the thought experiment, a powerful tool that has shaped our understanding of reality from the motions of planets to the paradoxes of quantum cats. When confronting something as elusive as a white hole, we cannot start with steel and glass. We must start with logic and imagination, constructing clean, hypothetical scenarios to test the boundaries of our theories. Picture, if you will, a simple probe. Its mission is to approach a classical white hole, to cross its event horizon and report back from the other side. According to the equations, this is an impossible task. No matter how powerful its engines, the probe would find itself fighting against the very geometry of spacetime. The horizon acts not as a wall but as a rushing, one-way barrier in the fabric of reality. The probe could fire its thrusters at full power, but it would make no progress, forever suspended just outside the point of no entry. Now reverse the perspective. Imagine a probe being created or launched from within the white hole itself. Its mission is to remain inside, to orbit that inner singularity. This, too, is impossible. The geometry within forces everything outward. The probe would be carried inevitably toward and then across the horizon, ejected into the external universe. These two simple mental images do more than describe an object. They define its essential nature. They make the abstract mathematics of a no-entry boundary tangible and clear. We can push this mental exploration further into the realm of cosmic accounting. Consider a hypothetical universe that contains only one black hole and one white hole, perfect opposites in eternal balance. At first glance, this seems like a closed, stable system. The black hole consumes, increasing entropy, while the white hole creates, seemingly decreasing it. But a thought experiment reveals the flaw. If these two objects were placed in the same universe, even light years apart, they would eventually interact. Radiation from the white hole would travel across the void and fall into the black hole. This single photon of interaction breaks the perfect symmetry. The black hole would grow slightly, its entropy increasing, while the white hole's effort to create order would be, in a cosmic sense, futile. The overall entropy of the universe still marches upward. This mental exercise helps clarify why white holes, if they exist, cannot be permanent fixtures. They must be transient events or exist in a state so isolated that this inevitable interaction is prevented, perhaps by being the exit of a wormhole to another reality altogether. This tradition of thinking with scenarios is a cornerstone of physics. Einstein did not discover relativity by looking through a telescope. He discovered it by imagining himself riding a beam of light. He clarified the equivalence of gravity and acceleration by picturing a man in a windowless elevator, unable to tell if he was stationary in a gravitational field or being accelerated through empty space. Schrödinger crafted his famous cat-in-a-box paradox not to suggest such a thing was real, but to expose the strange implications of quantum theory when scaled up to everyday life. These are not mere philosophical games, they are stress tests for ideas, revealing logical cracks and hidden assumptions before we commit to building billion-dollar detectors. For white holes, thought experiments serve as the essential blueprint. They take the raw, symmetrical output of Einstein's equations and ask, what would that actually look like? How would it behave? What laws does it challenge? The answers to these imagined scenarios then guide the mathematicians and the simulators, telling them which equations to solve and which signals to search for in the data. In the silent laboratory of the mind, we build the first fragile model of a cosmic fountain, preparing ourselves to recognize it should it ever erupt into view. That persistent, elegant symmetry is the thread that ties everything together. White holes are more than a single puzzle. They are a keystone idea, a conceptual cornerstone that connects entire wings of the physics cathedral. Their study forces us to abandon comfortable, compartmentalized thinking. You cannot understand a white hole by looking only at gravity, or only at thermodynamics, or only at quantum mechanics. You must consider them all at once. This is where their true power lies. They create a bridge between the smooth, geometric world of Einstein and the fuzzy, probabilistic realm of the quantum. The paradox of information loss at a black hole singularity is not a problem for astrophysicists alone. It is a crisis for anyone who believes the universe's rules should be consistent at every scale. By proposing a white hole phase as a resolution, we are forced to develop a language that can speak to both realms, a theory of quantum gravity. This quest unifies the study of the cosmos's largest structures with the behavior of its smallest particles. The fate of a galaxy may hinge on processes unfolding a trillion times smaller than an atom. Furthermore, white holes weave together the story of energy and the story of information. Thermodynamics, with its iron law of increasing disorder, meets information theory with its principle that knowledge can never be erased. In the life cycle of a black hole becoming a white hole, entropy increases globally, preserving the second law, while information is scrambled, stored, and ultimately returned, preserving unitarity. It is a single narrative that satisfies two of reality's most fundamental demands. This holistic view extends to the very origin of everything. Cosmologists studying the Big Bang and particle physicists simulating the primordial soup are, in a deep sense, investigating the same white hole event from different angles. One looks at the large-scale structure it created, the other at the particle zoo it might have produced. Whether white holes exist as tangible objects we can one day point a telescope toward is almost secondary to their role as an intellectual catalyst. The monumental effort to make room for them in our theories, to see if the universe allows such a perfect symmetry, has already driven progress. It has refined our questions, forged new tools in computation, and inspired cross-pollinating ideas between fields that once rarely spoke. This push toward a unified understanding where the colossal and the quantum, the past and the future, are seen as parts of a single, coherent whole, is the highest aspiration of fundamental physics. The white hole, in all its elusive beauty, is not just a destination for our curiosity. It is a guide showing us how to think about the universe in its complete, interconnected majesty. There is a quiet hum that remains long after the equations are solved and the data is filed away. It is the sound of wonder itself, a resonance felt not in the ears but in the mind. Our exploration has taken us to realms where time may fold back upon itself, where a crushing end becomes a radiant beginning, and where the universe seems to play by a hidden, cyclical logic we can only trace in fragments. This is not a dry academic exercise. To stand before the idea of a white hole is to stand at the edge of a profound and shared mystery. It touches something ancient within us, the same impulse that made our ancestors gaze at the stars and weave stories of creation and renewal. This sense of awe is our shared inheritance, a reminder that the cosmos does not belong solely to those who chart its mathematics. It belongs to anyone who has ever looked up at a clear night sky and felt a question form in the silence. Contemplating these cosmic fountains invites every one of us to marvel at the sheer improbability of existence. We are here on a tiny planet, using the curious mind's evolution granted us to decode the behavior of singularities and the birth cries of possible universes. That act of curiosity, that relentless need to ask what if, is among our most human traits. It has built civilizations, inspired art, and now guides our probes to the edges of the solar system and our telescopes to the dawn of time. Yet for all our ingenuity, the true lesson of the white hole may be one of humility. Each elegant theory, each sophisticated simulation, ultimately points toward a reality far stranger, more dynamic, and more magnificent than our current imagination can fully hold. The universe is under no obligation to conform to our intuition or satisfy our desire for neat endings. It may be a place of infinite renewal, of information forever preserved, of gateways we cannot see. And in that vast, unknown potential lies not frustration, but the ultimate source of wonder. The mystery is not a barrier to understanding. It is the very reason we continue to look, to think, and to dream. We have journeyed across a landscape of pure possibility, tracing the idea of a white hole from its elegant birth in mathematics to its potential echoes in the dawn of time and the silent voids between galaxies. This exploration has never been about a simple object to find, but about a question to live with, a lens that reshapes how we see everything else. It asks us to reconsider the finality of a black hole, the direction of time's arrow, and the universe's stubborn commitment to preserving every quantum secret. The white hole stands as a testament to the power of a beautiful idea, one that insists our reality might be far more creative, interconnected, and surprising than we have dared to assume. As physicist Jana Levin reminds us, the universe is a spectacularly modern puzzle, and the white hole is one of its most tantalizing pieces. It challenges us to keep looking, to keep questioning, and to remain comfortable with mysteries that outpace our current tools. So where do you think these cosmic fountains might be hiding? Do you believe they are the ancient architects of our cosmos, or the quiet destiny of every black hole, waiting in a future so distant it defies imagination? Share your thoughts in the comments below, and if this journey through the edges of understanding sparked your curiosity, consider subscribing for more deep dives into the wonders of space. Thank you for wondering with us. Until next time, keep looking up.